Hello everyone, welcome back to Math 110. In the last video, we used differentiation to construct an equation for the tangent line, which is a straight line. In this video, we will explore a far more interesting topic, which is maxima and minima of functions, and we will use the idea of derivatives to find the maxima and minima of a function. But first, we need to understand what maxima and minima of a function is. For that, we need to use a function. Let's say f is a function, and also it has a domain, say, with a domain D. Domain is the all possible values a function can take. All the inputs you can put in the function is the domain. This will help us define maxima and minima. Maxima and minima are two types. The first is global maxima and minima, and the second one is local. Let's see what they are. If f of x, if the function has values less than or equal to a for all x in D, the whole domain, in all of the inputs you can give, if the function has lesser values than f of a, then the value at a, then we call it a maxima. We call it a maxima, or more accurately, a global maxima. In the whole function, f of a is the largest value the function can get. Similarly, what is local maxima? It's the same, but local is valid, it's the same, but notice this, for all x, but in local it's in some small interval. It's in some small region. That value f of a is a maxima in that small value. We'll see an example of it and it will become more clear. So global, it's over all possible values. Local, it's in some range of value, some small range. Delta is a small, delta means, this sign is delta, it means small range, small number, maybe in a small region. This is a maxima. Again, if f of x has values greater than f of a for all x in D over the whole domain, all possible values, then we call it a global minima. Let me write minima, or more precisely it will be a global minima. Same for this, same, but we have a different interval, that is, and f of a would be minima, local minima. In some small region, this is the minima, and in the whole function, this is the minima. Let's see a graph of it and this will become more clear. Let's say we have a function. This is our x-axis, y-axis. Let's say this is the domain of the function. This is the set of, let's divide. This is the possible values you can put in the function, or this is the domain. Up to this value of x, I don't know what this value is, but up to this value of x, this you can put in the function, which is our domain. let's say at here we have this. This stops here. So what would be our global minima? Global minima would be this. Global, this one, global minima, this point, the point in the very bottom, because in the whole domain, all of the values you can give in the function, this is the smallest it gets. This is in a small region, let's say here to here, or maybe here to here, it's a local maxima. It's a maxima, but not the actual maxima, not the global maxima, but in a small region of interest, it's a maxima. So local maxima. Also, this would be our local minima. So let me write local, L stands for local, local minima. And this would be the global, G for global maxima. In the whole function, in all possible values of the function, this is the highest it gets. So this is global and local maxima. Now the important question is, since we are studying differentiation, how does differentiation help us get to these things? How do we know if there is a local minima or a global minima using differentiation? So let's see. Let's keep this. Let's get rid of these. Okay. There is a famous theorem of calculus which you can find in your book. I'll not prove it here. It's in every calculus textbook, good standard textbook, and also in your lecture notes, which says, suppose that f of x is differentiable at x equals to a, which is, you can find the you can take the derivative of x equal to a, that's what it stands for, and that x equal to a is a local maxima or a minima, then f equals 0. What does this mean? Suppose f of x is differentiable at x equals to a, and we know, let's say we know from this graph, let's say this, x equal to a, let's say this is x equal to a, we have a local minima or maxima, then the derivative is 0. First derivative is 0. That's what it's saying. Or let me put it in another word, if we know for sure that f prime of a equals 0, then we can guess, wait, there should be a local maxima or a local minima. So if the derivative is the first derivative at any point is 0, we can be sure there is a local minima or a local maxima. Is it a local maxima or a minima? We'll look into that in the next video. But here we know for sure there is a local maxima or minima. The proof is in the book. In the lecture note, you can look into it. So since we aren't proving the theorem, I can give you an example and see that this works. Also, I will look into a graph. Let's say I'll look into this graph and try to prove why this must hold. This is not a formal proof. This is an intuitive proof. But first, let's see an example. Let's say we have a function and we take the derivative, which is easy to find. It's twice x. Now, what is at which point is it 0? We can easily say that because it's 0 at 0, right? If you put 0 here, zero. So at x equal to 0, there should be a local maxima or a minima for this graph. Okay, good enough. So if you try to draw the graph, graph is something like this. At x equal to 0, we have a minima. If you draw the graph, you can see it's a minima, but this is the argument. So yeah, this is that. Now, let's try to see intuitively why this should be the case. That is, if the first derivative vanishes, there should be a minima or a maxima. Let's see why. Let's consider this. Let me erase this. We'll see both the cases. So let's say we don't know we don't know about this theorem, but we know about this graph. We know that this is a local minima and a local maxima, and this is a local minima. We defined differentiation as the slope of the tangent line. So let's draw the tangent line here. And also here. And so what does differentiation say? I'm just the slope of the tangent line, which is, let's say, slope of the tangent line, and slope is given by the difference of y coordinates and the difference of x coordinates. y2 minus y1, x2 minus f1. Okay, hold on to that for now. What is the slope of this tangent line? It has the same y value. So what should y2 minus y1 be? y2 minus y1 should be, let's write it here, it should be 0 because they have the same y value. Here they have the same y value because it's a horizontal line and the slope of a horizontal line is 0, and also because they have the same y coordinate, so the difference in y coordinate should be 0 for this tangent line. So it's 0. Same goes for this. This is a local maxima, this is a local minima. What is the slope of this tangent line? 0, because it's a horizontal line, and they have the same y coordinate. So we can say that using the idea of derivative, that since derivative is the slope of the tangent line and the slope of this is 0 and 0 at a local minima and a local maxima, so if the first derivative vanishes at a point, then we have a local minima or a local maxima. What is it? We will find out in the next video.